Welcome to my channel. My name is Said Ali Abbas and today we are going to discuss about Leibniz theorem. So what is a Leibniz theorem? Leibniz theorem basically helps us to find the nth order derivatives of a function that are equal to product of two functions. For example, if we have a function y, let's say it is equal to uv, means there are two functions u and v and both are in the product form. So if we have a function like this y equal to uv and we have to find the nth derivative of that particular function, so we are going to use Leibniz theorem for it to find the nth derivative of that particular function. So in this video we are going to prove Leibniz theorem through a technique known as mathematical induction. Then we will solve an example through Leibniz theorem so that you people understand completely and clearly how Leibniz theorem works and how we are going to apply on the questions to find the nth order derivatives. So let's start. So first we have a statement, let y equal to uv. Suppose we have a function y that is basically equal to two functions, one is u and second one is v, both are written in the product form. So we have a function y is equal to uv, where uv are functions of x and both possesses derivatives of nth order. Both u and v are basically depending on x and can be written as u is equal to u of x, means u is depending on x, and v is equal to v of x, so v is also depending on x. Both u and v are depending on x and they both possesses some derivative of nth order. They are not getting 0 in the first or second term, they have some nth order derivative, let's say. So in order to find the nth order derivative of that particular equation, or we may say that particular function, the formula, or you may say the Leibniz theorem, is this. It is known as Leibniz theorem. So what are the terms involving in this Leibniz theorem? Let's start from NC0. These C's you are seeing in the formula are basically combinations, and you are well aware of that. You can read NC2 as n choose r, and you are aware of the formula for NCR, that is basically n factorial over r factorial into n minus r factorial. N basically represents the total number of objects and R represents the objects to be selected from the total number of objects. So these are basically combinations. So in order to compute NC2 or NC1 or any NCs appearing in the Leibniz theorem, we are going to use that particular formula for it. So I'm not going in detail of what are combinations and what are difference between combinations and permutation. So NCR is basically this. So after covering these C's, we will move towards U and then V. So first start from U. So UN is basically the nth derivative of the first function U. So here these n represent the nth order derivative of function u, and v is a simple function, and in the similar fashion un minus 1 represents the nth minus 1 derivative of u, and so on. And same is the case for v. Here the v dash represents the first order derivative of v, and v double dash represents the second order derivative of v, and in the similar fashion vr is the rth derivative, and so on. We will get vn, that is basically the nth derivative of v. So it is known as Leibniz theorem. So how we are going to prove it? We are going to prove that Leibniz theorem through a technique known as mathematical induction. So let's take a quick overview of what is mathematical induction, then we'll start the proof. So here it is the short overview of mathematical induction. So mathematical induction is a technique that helps us to prove theorems or results are true for some natural numbers, positive natural numbers. So in order to prove some theorems or formula is true for natural number, we use one of the technique known as mathematical induction. So mathematical induction basically involves two steps. So we are going through these two steps to prove Leibniz theorem. The very first step is that we are going to prove that our statement, that is Leibniz theorem, holds for n equal to 1 and n equal to 2. We are going to check that is our statement is valid for the initial iterations, like for n is equal to 1 and n equal to 2. Then we will move towards the second step, and in this step we assume that our statement is true from some general number like n equal to r. We will assume that in step number 2 our statement is true for some n equal to r, and by assuming that we are going to prove that our statement is true for r plus 1th iteration, the very next iteration from r, you may say. So if we succeeded in proving these two steps, we will succeed in proving Leibniz theorem. So let's start from the step number 1. We are going to prove that our statement, that is Leibniz theorem, hold for some initial cases like for n equal to 1 and n equal to 2. We are going to put n equal to 1 and n equal to 2 turn by turn, and then justified that the formula, or that the answer we are getting from Leibniz theorem is in accordance to what we are going to prove through applying product rule on that particular function. So let's start. So in order to justify the very first step of mathematical induction, we are going to take the very first derivative of that function uv, that is basically equal to y. So what we are going to do, we will apply the derivative on that particular function uv, and we will see, or we will justify that what we are getting by applying the derivative on function uv is exactly the same that we will get when we will put n equal to 1 in the Leibniz theorem. So it will justify that by applying a product rule on this function, and the answer we are obtaining, and the answer we will get, is exactly the same that we are getting from the Leibniz theorem by putting n equal to 1 here. So first we will manually solve this function, and we'll find the derivative of that particular function uv. So we may write uv as brackets uv and dash. This dash is representing the first derivative, or you may say first order derivative of function uv. So as they are written in product form, so in order to take derivative, we are going to apply product rule on it. So what is the product rule? We have to take the derivative of the first function u, and it will become u prime, that is first derivative of u, and we are going to write v as it is, so v as it is, plus now second function, that is basically u here, u is basically first function. So after addition sign, we are going to write first function as it is, so here it is u as it is, and then we will take the derivative of the second function, so v prime here, that is the derivative of second function. So it is the answer basically we are getting after applying product rule on this. So if it is in accordance to the answer that we are getting by applying n equal to 1, that is by putting n equal to 1 in the Leibniz theorem, then we will say that our first condition, our step 1, or you may say our case 1 is justified. So when we put n equal to 1 in this Leibniz theorem, this nc0 becomes 1c0 u, and we are going to write 1 here for n, 1, v as it is, plus n again 1, c1 u, and n minus 1 will become 1 minus 1, and v prime as it is. So 1c0 is basically 1, so I'm not going to write 1 here. So the remaining will be u prime v plus 1c1 is again 1, so 1 is not written here. U 1 minus 1 is 0. 0 means no derivative, so we are going with simple function u, no derivative, and v prime here. So you can see that the step number 1, that is that we obtained after putting n equal to 1 in the Leibniz theorem, is exactly the same. The answer we are getting is exactly the same that we obtained after applying product rule on the function uv. It means that our step number 1 is justified, that this case holds for n equal to 1. We will write as that case 1, that is for n equal to 1, holds for our statement. Okay, now we are going to apply n equal to 2 here, and we are going to do similar steps again. So let's start for n equal to 2. So in order to prove our case number 2, that is for n equal to 2, we are going to do similar steps that we did for case n equal to 1. So now we are going to differentiate it second time, that is we are going to take second derivative of it, and again we are going to write it as uv double prime. Now double prime means second derivative. So in order to take second derivative of it, we are going to differentiate this equation number 1 again. As to get second derivative, we are going to differentiate answer we obtained from first derivative. So we are going to differentiate this again. So differentiating both sides, we will get this single dash is basically converted into double dash. That shows that it is basically a second derivative, and we have to apply product rule separately here. that is we have to apply product rule separately here and here too. So applying product rule here, we will get this first derivative, that is basically a first function. So differentiating again, it will become double dash, that is second derivative. Now the second function as it is, plus we have to take the derivative of first, we have to write the first function as it is, now u prime as it is, and going to differentiate the second function, that is v prime. It will become v prime, here it is v prime, so it is basically a product rule. So same will be done for this particular term. We have to take the derivative of that first function u, it will become u prime, and after and write the second function v prime as it is, plus now first function as it is, and we have to take the derivative of the second function. So this single dash will be converted into double dash as we are differentiating it twice or second time. So I wrote it as it is, and this term is also written as it is, plus 1 times of u prime v prime plus 1 times of u prime v prime will become 2 times of u prime v prime. So what we are getting over second order derivative is this. So now we will check that is over this equation or is over that particular answer is exactly the same that we will obtain, that we will get after applying n equal to 2 in Leibniz theorem. So when we apply n equal to 2, or we say when we substitute n equal to 2 in the Leibniz theorem, the equation for the Leibniz theorem will become, from here we'll start, we are going to substitute 2 here, so 2 c0, again we will replace this n by 2, u2v, and so on. We will get n2 here, 2 minus 2, and n minus 1 will become 2 minus 1. Just we will we substituted n equal to 2 here. 2c0 is 1. Again u2 and u double prime is the same. U2 means second derivative and u double prime also means second derivative, so don't get confuse yourself from these two notations. So v is exactly the same. 2c1 is basically 2, 2 minus 1 is basically 1, that is first derivative. V is again the same. 2c2 is 1, 2 minus 2 is 0, so I'm not writing 0 here as it shows a simple function u, so I'm going to write simple u here, and v double dash as it is. So you can see that the result we are getting by applying second derivative on the already differentiated function, that is uv prime, is exactly the same that we are getting by substituting n equal to 2 in Leibniz theorem. It means that our case, that our for case number 2, that is for n equal to 2, our statement holds. Our statement holds. So now, after completing the step number 1 of mathematical induction, now we will assume that over Leibniz theorem, that this equation, this Leibniz theorem basically holds for some general number, let's say n equal to r. So let's start. So now in the very last step, what we have to do, I supposed that the Leibniz theorem basically holds for some n equal to r. You can see that I have supposed here, let us suppose that above statements hold for some general n equal to r. So this statement holds for some n equal to r, we are going to suppose it that it is true. So what I did here, I just replaced all the n that are appearing in the above Leibniz theorem by r. So you can see that in this mentioned equation, all n are replaced by r. So we will assume that our statement is true for some n equal to r, and we are going to prove that it will be true for some r plus 1th iteration. So if we succeeded in proving that it is true for some r plus 1th iteration, it will put n to the proof. That means that Leibniz theorem holds for every positive integer, or you may say natural numbers. So in order to prove that this statement is true for some r plus 1th iteration, we are going to differentiate it again. We are going to differentiate this equation again, and then we are going to prove that it holds for basically r plus 1th iteration. So in order to start the differentiation process, you must know that the terms u r v, u r minus 1 v prime, u prime vr minus 1 and uvr, these mentioned terms are basically written in the product form. So when we are going to differentiate this equation, we have to apply product rule on all these mentioned terms as they are the product of two functions. So let's start. So differentiating this equation on both sides, this yr will become yr plus 1 because of derivative, and I'm going to write RC0 as it is. So RC0 as it is, and I have to apply a product rule on these two terms. So by product rule, I have to take the derivative of the very first function, that is UR, and it will become UR plus 1 as I'm going to take derivative of it. So this R will turn into R plus 1 because of derivative. So applying derivative on the first function, that is UR, it will become UR plus 1. I have to write second function, that is V as it is, plus now I have to write the first function as it is, that is UR, and have to take the derivative of the second function, that is V, and it will become V dash, that is derivative. It is known as product rule. So brackets close. I have to I'm going to do the similar steps on the second terms. So RC1 is as it is, and have to take the and have to apply the product rule on these two terms. So brackets, I have to take the derivative of this first function, it is r minus 1. So when you apply the derivative, you get basically plus 1. So if in order to apply the derivative on u r minus 1, when we add plus 1 here, this plus 1 and minus 1 will be cancelled, and all we are left with u r. So if we apply derivative on u r minus 1, that is first derivative, so this ur minus will become simply ur, because whenever we apply the derivative, we add 1 for instance. So in order to apply derivative on ur minus 1, we are going to add 1 in the power. So minus 1 plus 1 will be cancelled, and all we are left with ur. So here it is written as ur, and I have to write the second function, that is v prime as it is, plus now we have to write the first function as it is, that is ur minus 1, and have to take the derivative of the second function, that is v prime. So it will become v double prime or double dash, you may say. So this is the product rule on these on the second mentioned term. So I'm going to do the similar steps on this second last term and the last term. So two terms here. So I have already written the last two terms here after differentiating the last two terms. Now what we are going to do, we are going to simplify this equation. We are done with the differentiation part. Now we are going to simplify this equation. As you can see that there are some c's appearing outside the brackets here. We are going to multiply these c's inside the brackets with the terms inside the brackets. That is RC0 will be multiplied with the these two terms, that is ur plus 1 v plus ur v prime by distributive law. So you have to apply RC0 with these two terms here. So after multiplying RC0 with the very first term, you are getting this, and after multiplying RC0 with the second term, you are getting this. So after multiplying RC0 with both of these terms, you are getting these two terms. Same will be the case for RC1. After multiplying RC1 inside with the terms inside the brackets, you are getting this third and fourth term. Same procedure will be done for this. So I've already written here that after multiplying RCR minus 1 with these two terms, you are getting these two terms. And same for the case RCR, you are getting these two terms after multiplying RCR inside the brackets. As you can see, I have used green marker on some of the terms, and you can clearly see that these two terms basically on which I have basically used the green marker, urv prime and urv prime is exactly the same. So I'm going to take this urv prime as a common part. These two are basically, I'm going to take these two terms as a one part, that is I'm going to take common out of it. So after taking common urv prime, we are getting this, and the remaining part RC0 and RC1 will get inside the brackets like this. And in the very first term, I have replaced RC0 with R plus 1 C0. So it will not harm this particular term, because if you have 0 in the below section in the combination scenario, you will always get 1. So RC0 is equal to 1 and R plus 1 C0 is also equal to 1. So I may write it RC0 as R plus 1 C0. So I have modified this RC0 as R plus 1 C0 because the answer of both will be eventually end up to 1. So This term will get resolved with the term that will appear inside the dot. That is basically I have not written the term here. So after resolving the term, you will get this particular term, that is ur minus 1 v double prime, and rc1 plus rc2 that will appear in this dot section will resolve like this. So this will also get resolved with the terms here, so I'm not considering this. I'm going to take common from the other terms that are appearing here. So u prime vr and u prime vr is also mentioned here. These two terms also have some same part, so I'm going to take common u prime vr out of it, and the remaining terms inside the brackets, that is rcr minus 1 plus rcr. And the very last term is also written here, but with some modification. You are well aware of the property that if you have like MCM, it is always equal to 1. So if you have the value of n and r exactly the same, you are getting you are getting 1 always. So I'm going to replace this r and this r by r plus 1. That is, it will become r plus 1 and cr plus 1 in the very next steps. So I've already mentioned the property I'm going to use in future. So this rcr can be written as r plus 1 cr plus 1, as it will not harm that particular term. So now we have basically simplified to some extent this above equation. Now I'm going to use a particular property of combination to modify the terms appearing inside the brackets, and that particular property is basically this. When you have a addition of two combinations, that is ncr and ncr plus 1, this sum of two combinations will be converted into a single combination and can be written as n plus 1 c r plus 1. What we have done here, we have just added 1 in the above section, that is in the nth value we have added 1, that is it will become n plus 1, and same will be done for the rth value, and it is already written it as r plus 1, that we have added plus 1 for the rth value. So when we are going to apply that particular property, we are going to add 1 in the very first section, or we may say first combination. So applying that particular property here, this r will become r plus 1 and this 0 will become 0 plus 1. So r plus 1 will be r plus 1 and 0 plus 1 will be 1 only. So this sum will be converted into r plus 1 c1. So here it is r plus 1 c1, and the remaining terms I am quoting as it is, that is u r v prime. Same will be done for this. This r will become r plus 1 and this 1 will become 1 plus 1, that is 2. So it will become r plus 1 c2 and the other terms as it is. So r plus 1 c2 other terms as it is. You can do for this too. This r will become r plus 1, and when you add plus 1 here, as we are adding plus 1 above and plus 1 below, so when you add plus 1 here, this minus 1 plus 1 will get cancelled and you are getting r plus 1 cr only. So we will get r plus 1 cr only and the remaining term as it is. And I have modified this rcr as r plus 1 and r plus 1, as you know that rcr is also 1 and r plus 1 c r plus 1 is also 1. So I may write it as r plus 1 c r plus 1. So here it is r plus 1 c r plus 1 and the remaining term is as it is. Now you can see that after differentiating and simplifying, we are getting exactly the same result that we got from the Leibniz theorem. Like here it is, that green circle part is basically our Leibniz theorem for some nth derivative. You can see that n is appearing here, as we are proving for the r plus 1th iteration, that is for you may say r plus 1th derivative. So for instance, n will be replaced by r plus 1. So here it is, n is replaced by r plus 1, and you can see here is the derivative of for the case of n. For case n, that is we have n here, and its derivative keep on decreasing, like un here it is n minus 1, 1 less than n, then n minus 2 on n minus 2, and so on. It ends up to simple function u. And same is the case with our result, that is we have as we are going to prove for r plus 1. So r plus 1 here, after decreasing one value, that is after subtracting minus 1, we are getting r, that is one derivative less than the previous term, and so on we end up on the simple function u. So it shows that our result holds for r plus 1th value too. So now after proving that our result holds for r plus 1 value 2, you can write it as that this theorem holds for all positive integers. So I'm going to write it as the theorem. So this theorem, that is Leibniz theorem, holds for all positive integer. So this is basically the proof of. So let's talk about solving an example through Leibniz theorem. So I have a question here. Find the fourth order derivative with the help of Leibniz theorem. We are going to find some fourth order derivative with the help of Leibniz theorem. So I have a function y is equal to e to power x cos x, that is basically product of two functions, and the value of n is equal to 4. We can find the nth order derivative also, but the value the value I have chosen here is n equal to 4. So for n equal to 4, the Leibniz theorem that we have already proved will become something like this. I have excluded all the other terms appearing after nc4 as they are not required. That for case n equal to 4, we are just going up to nc4 here. So the formula for the fourth derivative with the help of Leibniz theorem will become this. Now what we have to do, we are going to put n equal to 4 here. So after putting n equal to 4, we will get the final formula to for calculating the fourth order derivative of that particular function. So I have already done that. That is, I have put it n equal to 4. So all the n's in this above equation are replaced by 4. Like you can see, nc0 is now 4c0, un is basically u for v. Same is the case for here, n minus 1, that is 4 minus 1, 3, and nc1 will have become 4c1, and in a similar fashion all the n are replaced by 4. So after substituting 4 in the above equation, the final equation to find the fourth derivative is this. So what we are going to do now, we are just going to put the required value that are appearing in this equation. That is the value of 4c0, u4 means fourth derivative of u, fourth order derivative of u, and v means the first order derivative, v means the simple function, and first order derivative is going to appear here, and the second order derivative for v here, for third order derivative for here, and the very last one is the fourth order derivative of v. So we are going to find the four derivatives for u, that is we are going to differentiate u 4 times, and same is the case for v, we are going to differentiate v also 4 times. So I have already done that. I have differentiated u 4 times, and the value for the u equal to ex will remain the same because it is a function, exponential function, and the derivative of ex is ex. So the fourth derivative for ex will be the same, and I have also differentiated the second function, that is v, basically cos x, 4 times, that is cos x after differentiating first time will become sine, then differentiating again will become minus cos, and minus cos after differentiating will become sine, and so on. So the choice of the first and second function is very important. So you have to choose a first function in the way that it becomes easier for you to calculate its higher order derivative. So I have chosen the first function as ex, and it is easier to calculate the functions of to find the derivative of the function like ex, that is exponential function. So now after I have all the calculated the values, I have calculated all the values, so I'm going to substitute all the values in their respective positions. So let's start. So after substituting all the values here, I'm getting this equation, and after solving that I'm getting the fourth order derivative of that function y is equal to minus 4 ex cos x. So in this way Leibniz theorem helps us to find the nth order derivative also, and like if we have choose n equal to 4, you may calculate for the value of n equal to 5, n equal to 6, and for some general value n equal to n, you may say for some n value. So here it is, we have proved the Leibniz theorem and we have solved the example through Leibniz theorem.